Okay, thank you very much. I would like to thank the organizers for the opportunity to be here. I've been learning a lot. And okay, what I will discuss is somewhat related to the subject of the conference, but not so inside the subject. So I'll try to give some explanations on why I chose to discuss this. So I will start with something which is very homogeneous dynamical, from homogeneous dynamics, which is trying to state and give an idea behind what's called Ratner's theorem. So let me state it. So let she a Lie group and lambda a lattice and phi t an unipotent flow on Xi over lambda. Okay, so unipotent flows appeared in, or at least elements of a group appeared in Jean-François' lectures. And so essentially this flow has this form. So phi t is ut of Xi lambda is something like this, with ut a unipotent one parameter subgroup. And so what this theorem tells us is that essentially we can really understand all the orbit closures and invariant measures of this flow. So it tells us that every orbit closure is homogeneous. This means that if I look at the orbit of a point, take the closure, this is H over where H is a subgroup. Okay? So it's homogeneous, and more than this, every ergodic invariant probability is also homogeneous, meaning that is hard in a subgroup like this. So this kind of result appeared in Min-Shu Lee's mini course, where some like even stronger statements were discussed, and my goal today is try to explain a little bit how the proof of this result goes, so and why it fails in other contexts, and to see what can we do in those contexts. So an important property of a unipotent flow, and it's even though I didn't define them, but the important property I want to keep about unipotent flows is that phi t is reparametrized by some other flow. In particular, if you take there's always some diagonal element or one parameter subgroup, so that you have a condition like this. I depends on S or something like this. And so this is a key property and the key idea to obtain this kind of result. And is to obtain extra invariance. For instance, try to show that this flow also preserves an orbit closure or a set. So when you have an element that normalizes your flow, you want to show. So for instance, let me explain. So example, let K be a closed phi t orbit, then we would like to know, and we want to show that AS of K is equal K for AS that normalizes phi. And the difficulty in general is that when we look something like this, we try to show that AS of K intersects K. So this is also phi t invariant. So if K is a minimal set, for instance, this already implies that the set is invariant by A. But in general, we don't know whether these sets are minimal, and that's why, in fact, in Ratner's theorem, in this full generality, one needs to first prove this ergodic property to obtain the other one. But the ergodic property has some difficulty, and so I'll try to explain this, how to get this extra invariance to see what can one do next. So let mu be an ergodic phi t invariant probability. And then one will choose, so and chooses some K compact with measure of K very close to 1. And if one chooses this compact set nicely, for instance, so that the averages, the Birkhoff averages of mu are very good and they converge quite fast inside K, then to show that AS star of mu equals mu, it is enough to show that AS of K intersects K. And so the question now is how one shows something like this. And this is the key idea for unipotent flows, is that one can control what's called the drift between orbits, and it has some polynomial behavior. So let me say a couple of words about that. So the key point is that close by orbits have polynomial drift. And by this I mean, if I take x close to y, then if I look at these 2 points, these 2 orbits, I'm sorry, they start drifting. So the first direction of drift is along the flow, direction, but the second fastest direction of drift is along the normalizer. So they drift along the normalizer of phi t at polynomial speed. And so here the argument then is that, okay, up to reparametrization, you know that phi t of x and phi t, let's say r of t of y differ by something which is approximately AS. And so since I chose a compact set, if I can choose the starting points in the compact set and the points where they are drifted to be in this compact set, then I can take limits and show this property. So the important thing is, since the measure of the set is very large, points will be returning to K with a lot of time. And since this drift by a polynomial, the distance they achieve will be good at most of the time. Okay, so that's the important thing of being a polynomial speed. So polynomials spend most of their time close to their maximum value.
But unless G is SL2, I mean, the normalizer of U is much bigger, so it's not going to be in A direction in general.
Well, so the A is not defined. So it's an element. So the point, what I'm only saying that I want to obtain some extra invariance. Of course, then this theorem is much harder, and then you need to see how to improve, and then you also need additional ideas to complete the proof. But this is what I wanted to say, because now I want to discuss what would be the analog of unipotent flows in some other context, and which kinds of results one can do in this direction, and why this kind of thing fails. Okay, so let me give the context. So this was kind of the introduction, and now let me consider the setting I will be interested in. So F, a diffeomorphism is said is partially hyperbolic. So this can be done for flows too, but I won't give the definition. And this condition of being partially hyperbolic it has a lot of resemblance with these Anosov representations. And so but here we have a diffeomorphism or a flow. So the flow, the cocycle over the flow in an Anosov representation has this property. And so if the tangent bundle of M splits into 3 bundles, which are the F invariant, so that there exists some L positive, such that for every x in M and vectors unit here sigma could be S, C, or U. One has that this differential of F to the L so what we are saying here is that vectors in this bundle get contracted by the tangent map. Vectors in this bundle are expanded by the tangent map. These are the conditions that you see with these ones here. But also you need that vectors here, they could expand, they could contract, you don't care, but whatever they do is smaller than what happens in the extreme directions. Okay? So this is the definition, and there's a fact. So there's a fact proven in the 70s, maybe by Hirsch-Pugh, that ES and EU integrate uniquely into F invariant foliations. Okay, so what would be the analog of a unipotent flow would be to try to understand, say, the leaves of the foliation tangent to EU. Okay, so maybe before I continue, let me say, so this setting is, there are plenty of examples that we've been seeing these days. So if you take some homogeneous dynamic in a compact quotient of a Lie group, then as soon as the adjoint representation has some eigenvalue different from 1, then you will get something like this. And one important thing about these flows or diffeomorphisms is that they are open in the C1 topology. So if you take perturbations of these, of the examples that we've seen these days, you get new examples. And now the unipotent flow, there is some continuation of it, which is the foliation tangent to EU. And the idea now is try to understand the topology and ergodic theory of this foliation. So the
HPS?
Hirsch, Pugh, and Shu. So, let me write. Okay. So the analog is leaves of. And so what I'll try to discuss is the problem of trying to describe the orbit closures or some relevant measures associated to these flows, to this foliation. So the property, we know that a leaf is normalized by F. Also with a similar property to this, that disks are mapped into larger disks. And there's another fact that I want to point out, which is due maybe to Pessin and Sinai, which says that there always exists some F invariant measures ergodic, which are absolutely continuous along the unstable foliation. So this means the measure mu has some disintegration. So this appears in Minshu's mini course. So and these are measures in leaves of WU, which are absolutely continuous. Okay, and so these measures have a name. They are called Gibbs U states. So the goal is try to see what can we say about the existence and uniqueness of these measures. Okay, so the analogy is not complete. So if you want, these measures are already invariant under F. So it's not F that we want to show it's invariant. So what we want to show is whether these measures enjoy some additional invariance inside the center direction. Okay. And so the problem would be can we describe the WU saturated and can we describe all Gibbs states? Okay.
So M is compact to Riemann.
M is compact. Yeah.
Okay, so the main difficulty to address this problem is that there's no way to put coordinates on this foliation so that leaves drift in a polynomial way. So we cannot use arguments like this, and this already fails in contexts which are very close to homogeneous. So this, so to give some history of the problem. So already in Teichmüller dynamics, so this is so already Ratner theory fails. So the techniques fail, but then there's this work by Eskin and Mirzakhani that still get a good description of these measures using things that did come from homogeneous dynamics. So the key idea to overcome this polynomial drift comes from some work in homogeneous dynamics. Without unipotents. And this is the work by Benoit and Kant. So let me explain this. So what they introduced is a different method called the exponential drift argument that is created to obtain things similar to this. So I will do a very brief comment because it's important to understand what are the things that we need to do. And so the exponential drift argument goes something like this. I say you have a point P, and Q, which are in the same stable manifold. So this is a stable manifold of P. And so when we iterate these points forward, they will be very close. So f to the n, take f to the n of P, f to the n of Q. So if we want to show that and we have the unstable manifolds here. Okay. So these are the So what we expect is that if we push a little bit to points close by here, let's call them P prime and Q prime. So the measure that we are studying is absolutely continuous here. So it looks more or less the same as we push, and it's invariant by this pushing. But if we are lucky, when we draw the stable manifold here, which I draw white here, so it comes somewhere over here, and it intersects in something that differs a little bit in the center direction. So when we iterate these points here for some time, so this point will get closer to here. And so we'll get this f m of P prime, and this f m of Q prime, which, if we are lucky, they almost differ by something in the center. So the point is that if we want to show that this is invariant under some movement along the center direction, we want to stop when this has some finite but macroscopic scale. So the difficulty here is that there's only one iterate when this happens. And so it's very hard to choose the points in a compact set so that when you stop here, you are in the good set that you want to study. But there is one important thing. So I'm putting things under the rug, but the important thing is you need these points here to compare the densities along the center direction. And so here, when they get shifted, you want to compare them here too. So you need to control the time you need to iterate. So, and to control this time, and here is the main point, you need to be very careful about what's this distance, okay? And so the point is that both in homogeneous dynamics and in Teichmüller dynamics, so these foliations are all very smooth, and these holonomies are all very smooth, and so you can really control this distance, and this gives some estimates on this that are enough to work. So the moral I wanted to give is that it's important to control the geometry of these foliations. And for general partially hyperbolic diffeomorphisms, the foliations are highly non-smooth, and the holonomies are highly non-smooth. So that's the difficulty one needs to address.
I think it's easier if you assume f is hyperbolic instead of partially.
Yeah, it's easier, and I will at some point. But here, the main point is that I want to distinguish the unstable direction I'm studying and the center direction where I want to get some additional invariance. So as you notice, so here I said this is growing. So I need some expansion along the center. And even if I assume that the center is expanding, this is a difficult problem. And in fact, it's all the problems I know how to deal with. Okay, so let me mention some results in this direction. So there's this work by Asaf Katz that also has some version done by Alvarez, Leguil, Obata, Santiago, and recently also Brown, Eskin, Hertz. That try to adapt this argument to the partially hyperbolic setting, but they require some geometric condition, as you can see, and the geometric condition is that essentially the distance along the center of P prime and Q prime is more or less the distance of P to P prime to some power. Okay, and they call this, and for the condition is very technical, but they call this quantitative non-integrability. It's a technical condition. So what I want to explain is a result. So it's the conclusion. So this is based on some joint work with Alex Eskin and Sichuan Zhang. And I will state one result that we have, that it's the easiest to state, and it relies on some other work of other people. So let me state it as follows. The theorem is by Avila, Courvoisier, and joint with and the result is the following. So let F be smooth and also partially hyperbolic diffeo with EC expanding. This means that for the center direction, we also, if we wait a little bit, we'll see twice the size. And this implies then F is hyperbolic, it's a nozzle. And then the result says then either ES plus U jointly integrate into C1 foliation, or there is a unique Gibbs state, which coincides with the SRV measure. Okay, so this is the result. So we have some more general results, but I think this is the easiest to state, and in particular, it implies the minimality of the strong unstable foliation, which wasn't known, but in fact the minimality is used to get this. It's not like in Radner we use the fact that the foliation is minimal to get the measured classification.
So, sorry, you say F is another form?
F is a nozzle, yes. It's a nozzle, but the unstable bundle splits into two bundles. And we are looking at measures which are smooth along the one-dimensional foliation, and we are getting that they are smooth along the two-dimensional one. Yes. Yeah. And that's the SRV condition. Okay, so I have some time, and I will try to explain a little bit more about the Eskin-Mirzakhani scheme and how to do some ideas on how to do this. Okay, let me say. Okay, so we have mu is.
What about T2 case?
In T2 case, the thing is already the Gibbs state are the best you can hope for. Okay, because they have to be, you want them to be smooth along the highest dimensional direction possible. So if you're in T2, you have the stable and the unstable, so the Gibbs state already exists and are already SRV. So this is kind of the first non-trivial case. Okay? Yes, thanks.
So you didn't say explicitly, but the answer to your problem is known for another flow if you take for EC just the direction of the flow and EU and ES, stable and unstable foliation?
Depends. If you take the full unstable, yes. So yes, yeah. So here the main point is to use.
This is what I was saying. Yeah. Okay. Yeah. This is on this case.
Okay. So you take an F invariant gives you state, and what you obtain is this family.
Excuse me? Yes. So why is this fact about another foliation, another automorphism when you take the full unstable foliation, saturated leaves are everything? Why?
Okay, because so Pesin and Sinai already showed that you have something with the SRV measure is the Gibbs state. So essentially the translation of that problem to this case would be can u-Gibbs states be promoted to SRV measures? So if you are already, your U state is already an SRV measure, there's nothing to do. Okay, and maybe another comment to explain that. So if F is volume preserving, what we are showing here is that the U states are the volume. Okay, because that's the unique SRV measure. Okay.
The OR is exclusive?
No, and in fact, the problem is we don't know how to deal with the first case. Okay. So this case can happen. So for the linear map, you know that this integrate, and this is really infinite codimension. It's very uncommon that you have this, but in principle, you could have this, and that there's more than U state, and we don't know that. And yeah, thanks. Okay, so if we place ourselves in this setting, so all the bundles are one-dimensional. We are in dimension 3, and that's important for the following reason here, is that there's a good family of coordinates, not as good as to get polynomial drift, but is good enough, and the point is so there's normal form coordinates. This means that a family or a map from M continues so that phi xt belongs to the local and stable manifold of the point X, derivative, say, it's It's a given. And we have this property of reparametrization property. For small. So we really get some coordinates on which the action of f is kind of affine. And the good thing about these coordinates is that when, and this is kind of a consequence, let me state it as a fact here. This maybe can be attributed to Le Drapier-Young. Is that in these coordinates, mu u is okay, and so we what we want to do is to address this property here. And so what we will do is to look at two close by unstable manifolds and look how the stable direction varies along the unstable manifold. So and this is, okay, so I need to mention this. So this is an idea that appeared templates. And this is something that we had to develop, but the idea starts with in a paper by Sushi and Zhang on exponential mixing. For Nozzle flows. Which shouldn't be too surprising because the difficulty to show exponential mixing for Nozzle flows is very similar to this. You need to control non-integrability of these things. And also let me mention that there's this work by Foulon Hasselblad that I just could look yesterday, but it's related to and gives another interpretation of kind of the same idea here. And the point is like this. We want to draw an unstable manifold here, so through a point x, and we look at a nearby point in the same stable. So we have the unstable here. And so if we want to control the geometry of this, we want to look at the vectors. So these are the ES bundle along this unstable manifold. So you get a family of directions, which is a good first order approximation of where this unstable manifold will hit here. And typically, you expect this to be a very horrible curve here. It's only Holder. So the key observation is that this will be the case at every scale unless this is much smoother than you expect. So that's a key observation. Right, where? Over here. And this is, I like to think this as related to this, which is in normal form coordinates, either ES is described by a polynomial everywhere, or it is very non-smooth at every scale. Of fixed degree. So essentially what we are saying is that there's a finite dimensional family of possible directions here, so that if in some point this projection is smooth in a small interval, then everywhere it has to belong to this finite dimensional family. And if you are not in this finite dimensional family, so the ball in this family is a compact set, and so you will be, if you approximate this unstable by a polynomial, then this has to be far of the polynomial at every scale. Okay, so that's the key observation, and so let me say, yes, see if I can explain a little bit why this is the case. Okay. So why? Yeah. And I won't have time to explain it entirely, but let me at least explain what I mean by this object varying here, and why you can expect maybe it's a polynomial. So you have this thing, and to each point in the unstable, have x here, you're looking at the stable at each point. So you can think of the stable direction as a section of some bundle over the interval. So because essentially we will mod out by this unstable direction, and we will take ES of t to be the direction in t phi x. So let me call it E xt of m modeled out by the unstable direction, because we don't care about how this moves in this direction. And so this is a two-dimensional bundle everywhere. And the fact that this map is, you have a diffeomorphism that preserves this drawing, gives you an action. So you get a bundle action on this bundle of here by applying the derivative of f. And in 2 minutes, the point now is that when you look at this and you want to solve the equation for this stable bundle, typically it won't converge. So you get some, you don't get the right contraction conditions that you get usually to find the unstable manifolds or things like that. But the key point is that if you take enough derivatives, so the formula you get is getting multiplied by the unstable direction, the inverse of the unstable direction. So if you take enough derivatives that only depend on some Lyapunov exponent of this map, you'll get a contraction. So you don't solve the equation, but you solve it up to polynomials. And that's what gives essentially this dichotomy to control the geometry. Okay, so that's what I wanted to say. Thanks.
Are there any questions?
Yeah, I want to understand your picture. So your picture is in T3.
Yes.
And so at each point there are two unstable leaves, one which is one-dimensional and one which is two-dimensional.
Yes, this is like the two-dimensional.
This curve is drawn in the two-dimensional leaf.
In the two-dimensional leaf, yes.
Okay.
Yeah. So I'm kind of projecting along the stable, and then you get a very bad.
Did you say you use this exponential mixing?
No. We use this idea that appears. Yeah.
Other questions? So let's thank again. Yes.
I was under the impression that any three-manifold that commits in an alpha flow has like its fundamental group has exponential.
Yes, that is true, but this is a diffeomorphism. Okay, so and in fact you have the linear example. So you take a matrix without eigenvalues 1, and it induces a diffeomorphism on this, and so you perturb it, and we are trying to understand this perturbation. Yes.
Okay, so let's thank again the speaker.